thank you for the invitation to allow me to present you the R2D2 project, which is a Xenon TPC to look for neutrinoless double beta decay. So first, I will introduce quickly the physics of the double beta decay, and then I will present you the result we have with our prototype, and we made also simulation for the full experiment. So what? It's
click on the zombie first.
Yeah. Okay. Thank you. So the search of neutrinoless double beta decay is related to the determination of the nature of the neutrino, because the neutrino can be a Dirac particle. In this case, neutrino and antineutrino are distinct particles, or the neutrino could be a Majorana particle. In this case, the neutrino and the antineutrino are the same state. And this has a huge importance for particle physics to understand the generation of the neutrino masses through the Higgs mechanism, but also in cosmology, because in the leptogenesis model, it is required to have Majorana neutrinos. So for the double beta decay, it exists different type of double beta decay. There is a two neutrino double beta decay. In this case, you have emission of 2 electrons and 2 antineutrinos. This is just the single order of the single beta decay. And this does not give any indication of on the nature of the neutrino. What could be much more interesting is the neutrinoless double beta decay, which can occur only if the neutrino is an antiparticle. And there is the Schechter-Vallée theorem, which says that if you observe the neutrinoless double beta decay, you are sure that the neutrino is the Majorana particle. And in fact, it exists different possibility to have neutrinoless double beta decay. You can have a light neutrino exchange, you can have heavy neutrino exchange, you can have Majorana emission, but and also other processes which are beyond the standard model. And in fact, to look for neutrinoless double beta decay, you open a door for the neutrino physics to look for the neutrino mass hierarchy, the absolute neutrino mass, the right-hand current interaction for neutrino, the CP evaluation in electronic sector, search for supersymmetric particles, and so on. So this is in fact, neutrinoless double beta decay is really very rich physics. So experimentally, what will be the signature? The first signature is the emission of 2 electrons. And also, if you look for the distribution of the sum of the energy of the 2 emitted electrons, so you should, for the neutrinoless double beta decay, as the energy will be given to the 2 electrons, you should observe a peak at the energy of the transition. Then for neutrino double beta decay, because the neutrinos take a part of the energy, you will have a continuous spectrum in the sum of the energy of the 2 electrons. And this is in the case of Majorana emission. In this case, we have also a continuous spectrum because the Majorana will take a part of the energy. But you can look also for the other kinematical variables. This is an example if you are able to measure the angular distribution of the 2 emitted electrons. This is the case. This is the case for the light neutrino exchange, and this is the case of in the case of existence of right-handed current. So in this case, you can distinguish what is the process if you observe the neutrinoless double beta decay. We have to take into account that we can have decay not only to the ground state of the daughter nucleus, but we can also have decay to the excited state. And in this case, you have 1 or 2 additional gamma rays, and this can help to remove a part of the background. And the final, observable would be to detect the daughter nuclei, and this maybe could be done in the case of Xenon. So it exists in the nature about 35 double beta decay meter, but experimentally, there is only about 10 isotopes that you can use. Because first of all, you need quite high transition energy for two reasons, for the probability of the process, but also because of the background coming from the natural radioactivity. And also you need quite high natural abundance in order to be able to enrich the material. So today, the two neutrino double beta decay has been observed for all these isotopes, and it ranges between 10 to 18, 10 to 21 years, depending on the isotope. But today, we did not yet discover the neutrinoless double beta decay, and the limits are, for the period, is about 10 to 25, 20 to 26 years, depending on the isotope. So theoretically, the inverse of half-life is proportional to the phase factor, to a nuclear matrix element, and to the effective neutrino mass that you can measure through the neutrinoless double beta decay. And this value, the phase factor and the nuclear matrix element, depend on the isotope. Here you have a function of the isotope, you have the phase factor, and you can see that the most interesting isotope from this point of view is neodymium 150. You don't know how to enrich it at high mass. And for the nuclear matrix element, you can see that there are a lot of modes to calculate them. And in fact, there are large discrepancies, and it's why then we will give the limit on the effective neutrino mass. We'll give a range to take into account the different value of nuclear matrix element. And the main problem when we are looking for neutrinoless double beta decay is the background, which is coming from the natural radioactivity. Here you have the different isotope. This is the energy of the transition. And here I put the maximum energy coming from the decay of these isotopes that you have in the nature. And you can see that depending on the isotope, you will have a different contribution of the background. But for all the isotopes, you will have background from the natural radioactivity. And also you can have a background from the cosmic rays, especially from muons. But you can also have a background from the alphas, which are in the material. And at the end, the ultimate background can be the two neutrino double beta decay, because if your energy resolution is not good enough, you can have some events coming from the two neutrino double beta decay under the peak of the neutrinoless double beta decay. And there are different strategies to eliminate this background. It is like for dark matter. You will screen the material. You will try to have an excellent energy resolution, as I said. And the identification of electrons is something which is also very important in order to reduce the background. And you can have active veto and so on. So, and the sensitivity of the experiment, sorry, this is the experimental sensitivity. So it will depend on the efficiency, on the mass of isotope, the time of exposure, and the signal upper limit. And why I show you this formula is that the signal upper limit depends on the experimental background. And if you have no background, the signal limit will be constant, and then the half-life limit will be linear with the exposure. But if you have some background, in this case, the half-life limit will depend on the square root of the exposure. And just to illustrate that and to show that it is important to try to get background-free experiment, is that this is the exposure in ton per year. If you have zero background, you have a linear dependence. But as soon as you have one event, you will lose in sensitivity quite quickly, and you will saturate rather quickly. So it's why to have zero experiment is something which is important. What is the status today? Quickly, so there are different types of experiment. There are the pure calorimetric experiment with an excellent energy resolution. This is Legend and with a germanium detector, and Cupid with bolometers. You can play with large mass. This is a case of KamLAND, where they dissolve 800 kilograms of Xenon 136 in liquid scintillator, and also EXO 200 working with the liquid Xenon. And for the tracking experiment, which has the capability to see the two electrons, there is a SuperNEMO, where you can see the tracks coming from the source foil with a tracking device and calorimeter to measure the energy. And you have next white, which is also a TPC, which is where they are able also to see the tracks. But the problem is that is a number of electronic channels which induce a large background. So, and today, what are the sensitivity for the different isotopes? So you should consider that for all this square, in fact, it's like that. There is no, don't take into account the scale here. This is the effective neutrino mass that you measure with the neutrinoless double beta decay, and this is the lightest neutrino mass. So today we don't know if the lightest neutrino is M1 or is M3 for the 3 mass of neutrino. And you have two areas. If M3 is the lightest neutrino, you have this band, and if M1 is the lightest neutrino, you have the red band. So today we started to investigate what we call the inverted hierarchy with the Xenon, and the most sensitive experiment today is a KamLAND. And for the next generation, we want to rule out the inverted hierarchy and start to explore the normal hierarchy. So now I'm going to R2D2. So if you want to make a neutrinoless double beta decay, what are the main requirements? You need to have the identification of the electron. You need an excellent energy resolution, a low background, and a large mass of isotope. And the question is, can we meet all these requirements at the same time? And this is the goal of R2D2, which stands for rare decay with a radial detector. We started to work on this program in 2017, and our goal is to have to set up a detector able to reach a zero background with a ton of Xenon. And for that, we want to use high pressure Xenon TPC. And why we want to use the high pressure Xenon TPC is that Bolotnikov and Ramsey demonstrate in more than about 30 years ago that the resolution is very good with Xenon up to 60 bars. It's good and constant. And after, because you start to have a liquid phase, the resolution is not so good, but at least up to 60 bar in gas, you can have an excellent energy resolution. This is energy resolution for the cesium at 650 keV. And so we consider at the beginning, we consider two options for the design of the experiment, because at that time I was working on the new G experiment to look for dark matter, and it was a sphere which was proposed by geometries. You fill your sphere with a gas, and inside you have an anode, central anode, and you apply the high voltage on the anode, and you drift when you have an event with ionization of electron, you drift your electrons to the anode, and you have an avalanche region, and you record like that the energy of the event. But you could have also the solution which is cylindrical with just an anode at the center and a cathode as a cylinder. So and what we saw that we have an excellent energy resolution with such a detector. We can have an extremely low background because we use only one channel. In most of the experiments, the background is coming from the electronics. So by using one channel, you win on the background. You can make a large detector, and the detector is by nature is very simple. So And in fact, we compare the two geometries, and I go directly to the result. In fact, we use the cylindrical design because of the advantage compared to the cylindrical one. So what is the history of our R&D? First, we start with the first. At the beginning, we made the spherical TPC. So it's a cylindrical inside, but we cannot go to high pressure. But we already checked that with alpha rays by comparing the track length of alpha rays from 200 millibar to 1 bar. We saw that we have the same energy resolution. So it means that the energy resolution does not depend on the length of the tracks. This was a very encouraging result. First of all, the energy resolution was good, and it does not depend on the track length. We built a second spherical TPC, 35 to 40 bars. And in this case, we saw that we have also an excellent energy resolution up to 3 bars with argon, but we were limited by the high voltage at 4,000 volt because in the design of the spherical TPC, we have the anode with the rod, and we had a spark between the anode and the rod. So it's why we are limited at 4,000 volt. And this was one of the reasons why we have the spherical design. Then we built the first cylindrical TPC. But it was not certified for pressure, but we started with some results to make some measurement with argon and xeno. We got quite a good energy resolution, and we demonstrate that we can have the same resolution with argon and xeno. And this is quite important, as I will tell you in the future. And finally, we have cylindrical detector. And I will present you the result for this prototype now. So there is also something which is very important, is we can operate the cylindrical TPC in 2 modes. In ionization mode, it means that we just drift the electrons, and then we have no gain when we arrive on the anode. Or we can work in proportional mode. In this case, we have an avalanche near the anode, and we have a gain. So, and in fact, to understand these 2 modes, we have to come back to the Shockley-Ramos theorem. It says that the signal that we observe is a current which is induced by the charge moving inside the gas, and the charge creates an induced current that we measure. And just to explain you, at the beginning we worked in proportional mode, and but we had some troubles because you are obliged to work at high voltage compared to the ionization mode. And I will show you what are the advantages to work in ionization. So here you have the time. This is the position of the event, and this is the induced signal. And start. So imagine that you have an event here at t equals 0. So your electrons are moving beyond the threshold, which is here. Then the signal induced by the electron is below the threshold. So and your electron reaches the anode, and the signal ends. And what is important in this case, as you start to record the signal, then your charge starts to move. This time corresponds to the radial distance of the event. Now, if you are working in proportional mode, your threshold is higher. So if you have the same type of event, during a long time, for the electron and for the ions, the induced current is below the threshold. And you just cross the threshold near the anode. And in fact, the signal that you will record will come from the ions which are created in the avalanche. So in this case, you lose you lose the position of your events in the radial position. You can extrapolate, but it is not as precise as for the ionization. So it's why we decided to work in a ionization mode. So, and also you have a better energy resolution because in this case you don't have the stochastic fluctuation which are due to the avalanche process. And something which is very important, if you are working in a proportional mode, if you want to have a 1% energy resolution, imagine that you use a wire which is 50 micrometer diameter. In this case, you should have an homogeneity of the surface which is 1%. For a wire which is 50 micrometer is not obvious. In the case of in ionization mode, you don't care about that, about the inhomogeneity of the surface of the anode. And you have also less impact of electronegative impurities because when you are working in proportional mode, the impurities that have a role which is much more important in the avalanche that when you collect the signal in ionization. And also, you work with a less high voltage. And in fact, as I will show you, you can work not with wire, but with a rod instead of wire in ionization. So this is, again, the photo of the prototype here. And so first of all, we check that we have not too much degassing, because to avoid to have electronegative impurities. And we test a different type of anode. Maybe you cannot see it, but here, this is 50 micrometer wire. This is 1.2 millimeter wire, and we use directly a rod in copper. So we go to the shop and just we buy part of a copper tube, and it works immediately. To make our measurement, we use a polonium-210 alpha source of 5.3 MeV. At the beginning, we put the source inside the detector, but we saw that we have a distortion of the field, and the resolution was not, it affects the resolution. So finally, we decided to make a hole, and we put the source on the external part of the cathode. Why I say that is because in the result that I will show you, we have to take into account that it is not a perfect system because some of the alphas can also interact with the shape of the hole, and we can have a degradation of the energy of the source. But we can use also the radon that we can introduce in our detector to measure the energy resolution in the volume. So we have a source and we have the radon. So we work on the purity of the gas, but today our system is limited to 10 bars, and now we want to go to 40 bars, and we are developing another system. This is just to show you that it is working. So here we stop the recirculation of the gas with the purification. We saw that we lose part of the signal, and when we restart the recirculation, immediately we come back to the previous level. So that was the fact that it was working. But we saw also that we have a problem of vibration, but we know that we can arrange that. And a way to measure the gas purity is to measure the electron lifetime. And we know that our electron lifetime is not very good, but we know that we have a room to improve the purity, and this is done in liquid argon and xenon very well. So we are not very how to say. We think that we can really get a good electron lifetime and to have a good gas purity in the future. And what I show you is the results are quite conservative because we know that we can really improve the purification of the gas. I will go quick. So we have the electronics, and I will not show it. So one of the problems in this detector is that you can see the detector like an antenna that you put in the volume of xenon. So this is the most simple thing that you can do. But if you are speaking about antenna, of course, you are collecting a lot of noise. And this is what we can see here in the frequency spectrum. And in fact, we have here the mechanical vibration, and here we have the perturbation from the electrical network, because we are colleagues which are also working. But we made the test, and now our system is on battery. So we really solve a part of this problem, and we still have to work on the mechanical vibration. So for the signal, in fact, in ionization, our signal is very rich, and I want to show to demonstrate that. So this is the raw signal. Okay. This is a deconvoluted signal. And so, as I said, as soon as you go over the threshold, you can record the time up to the end of the event, and this gives you the radial position. The width of the signal gives you an indication of the direction, because imagine that you have the if the detector is horizontal, you have the anode here, and here you have the track. If the track is like that, perpendicular to the anode, almost all the electrons will arrive at the same time. Now, if your track is going to the anode, in this case, you will have a different time between the beginning of the tracks and the end of the track, and then the width will be larger. So that give you an indication of the radial extent of the track. And if you reintegrate the signal, in this case, you can measure the charge, which is the reconstructed energy. And this is typically in blue, you have an experimental signal, and in orange, you have a simulated signal taking into account the geometry of the detector, the gas, and all the physics that we can, and also the electronics, the effect on the electronics of the signal. This is something to show that our detector is very powerful for the position. These are data with the 3 bars, and here you have the charge, and here you have the time. So it means that the anode is here and the cathode is here. So what you see here, you have the event coming from the cathode, and you have the event coming from the source here. And in fact, we understand that these events are coming from the radon, which is in the volume. And these are also the daughter of this is the source that we have behind the cathode. These are the radon events in the gas. And these are the daughter of radon. You have some of the daughter of radon decaying in the gas, but some of them have the half-life is large enough to have some of the polonium-210 on the cathode, and also you have the polonium-240. So it means that we are able really to distinguish the vertex of the event in the detector. And this is again the energy as a function of the width of the signal. And in fact, you have in this region, these are the tracks which are orthogonal to the radius. As I said, these are the, if you have your anode here, you have tracks like that. And in this region, these are the tracks which are going to the anode. So you can have an idea of the direction of the track. So this is the energy resolution that we get here. again, it is not optimal because the gas purification is not optimal, the electronics is not optimal. And as you can see, we have a tail on from the alphas, which are pointing to the fact that some of the alphas have an interaction with the shape of the hole on the cathode. And this is for the radon, which is in the volume. And you can see that we have an excellent energy resolution, even if not all is optimized. We have also a new result. We took data with now 16 bars. And what we wanted to see is what we call the BIPO effect. It means that it is a decay with a beta ray to polonium. And you have after you have a delayed alpha from polonium to bismuth. And you can see that we are able to distinguish the electron from the alpha. And we have still an excellent energy resolution for the alpha. And we can measure the half-life, which is, we expect 164 microseconds, and we measure 167. So it means that we are able to distinguish electron from alpha. And also we are able to see all the alphas coming from this chain with an excellent energy resolution. And if I show you the same plot, which is the energy as a function of the position, here you have the anode, here you have the cathode, you can see that we are able to see the event coming from the cathode. The source is here, and here you have the decay of radon inside the detector. So at the end, for the energy resolution, this is the resolution as a function of the pressure. In red, it's with argon. In blue, it's with xenon, and with different type of anode. And you can see that we have an excellent energy resolution for the source, but also for the radon in the detector. And this for us is very promising. And we know that the resolution is mostly independent on the gas nature. It means that we can commission the detector with argon before to use xenon. And as we expect, it was demonstrated by Bolotnikov et al., the resolution is mostly independent on the gas pressure. And the resolution is similar if you have a point-like source or a diffuse source. So now we are working to make a vessel using a composite material. This is to have the lightest detector that we can imagine, and to be able to afford 40 bars, you need a composite which is 2.5 millimeters thick. So it means that at the end, the detector will be only 60 kilograms. The weight of the detector will be only 60 kilograms. And today, but of course, the difficulty will be to have a low background composite. It means to have less than 10 microbecquerel per kilogram in uranium and thorium. And this is the challenge, and it's why now we are working with a company, and we are selecting materials to try to reach this challenge. But today, to make a test, we bought an industrial composite vessel, which is for hydrogen storage. And we have now this in the lab, and we will start soon to take data with this vessel. This is to demonstrate that we can drift over 50 centimeters, because our setup today we can drift on 11 centimeters, and we want to increase the scale. So I will just show you quickly what the extrapolation of our R&D to a full detector. So we made a simulation, and for that we suppose that we will read the signal at both ends of the anode. Up to now, we read the signal just at the top, so we don't have the Z position, but we suppose that we have a resistive anode and that we are able to read the signal on both ends. And also, we use an ASIC-based current amplifier, and this has been already produced and we are in test. And so based on this assumption, I will show you what are the results of our simulation. So we use geoneutrinos. For the drift time, we use Garfield, and at the end, we use the Shockley-Ramos theorem to reconstruct the energy deposit. And in fact, we can decompose the signal with all the deposited energies that we have in the detector. So this is from the simulation, and in fact, you can expect to see the two electrons like that. So, and this is an event, typically an event of background. This is a simulation from thallium where you have gamma rays which interact in different parts of the detector. And if you record the deposited energy as a function of the time, you see that you have a different deposition of energy inside the detector. And this is a zoom on this part. So, okay, I will go. We can, okay, this is a detector that we simulated. So it's with almost 600 kilograms of xenon, and you can see that the experiment is quite small. We suppose that we use a shielding of copper and lead, but of course, for us, the best solution will be to put the detector inside a large tank of water. So at the center, we have an anode with 1 centimeter radius. We have the readout on both sides. We have the xenon, and we have the cathode, which is sorry, the vessel. And inside we have the cathode, which can be very light because we think to use 200 micrometer aluminized mylar where we will apply the voltage. Something maybe that I forget to say is that we apply the high voltage on the cathode. It means that the anode is at the ground, so this is much more better for the signal. And what we want to develop, as I said, is a vessel in using carbon fiber and epoxy. And we are working with a company which is in Nantes in order to develop this new composite. Okay, the shielding, this is not the most important. Okay, so we made the simulation, and the signal simulation, as I said, is based on what we have on our prototype. And we have also the signal reconstruction, where we deconvoluted the signal in order to see the different observable. And we reconstruct, in fact, each deposit of energy in the signal decomposition. So for one of the difficulties energy smearing, of course, when you are doing a simulation, the intrinsic energy resolution is 0.1%. If you add the stochastic fluctuation, we have 0.3. Bolotnikov et al. Shows that at 660 keV, 0.5%. So, and in our prototype, we had 1% at 5.3 MeV, but as I said, it is not and it corresponds to 1.5% energy resolution at the energy transition of the Xenon 136. So for the simulation, we consider that we can reach 1% energy resolution. So, and you see, this is typically the signal that we will expect, where the event with the 2 electrons at 40 bar should be localized in the Z direction, but also in the radial direction. Then, for a part of the background, it will be a multi-compton, where you expect to have a longer delta Z and longer delta R. So first of all, we simulate the signal, and then we decided about the RY, and it's about an efficiency of 80% of the event. It means that some of the electrons are reaching the cathode. In this case, we lose the event. And in fact, we have 5 variables for the moment to select the signal and to reduce the background. This is the number of peaks that we reconstruct in the waveform, and with this cut we can reduce a part of the background. It's the same for the delta, the maximum radial distance between the reconstructed peak, and so I will go quickly on this because this is quite technical. But we have we can make some cut in order to reduce the background, and in particular the multiple quantum coming from the gamma rays. And if we add the topological cut, we still keep 60% of the signal, which is quite important. And most of the background is coming from the radioactivity of the vessel. And we made the simulation supposing that we can reach 10 microbecquerel per kilogram, and it corresponds to this number of background that we will expect in the detector if we are at this level. And we check also the background coming from the radon, and for that we use what was reached by NEXO, Xenon, and Prof, and we think that it's quite conservative to suppose that we can reach 5 microbecquerel per kilogram, because in the other experiment it's typically this number or below. Also, one of the problems for the Xenon is the cosmogenic nuclei, but if we are at the depth of LSM, it will be a background which is really negligible. So at the end, we took a lot of possibilities of the background, and most of the background is coming from the composite radioactivity. But for the composite radioactivity, at that time, we decided to make a 2 centimeter thickness for the composite, because we don't know what was the value that we can reach. But now we know that we can reduce it by almost factor 8 or 10. So it means that we can really reduce this if we are able to reduce the 10 microbecquerel per kilogram. And we check also that the event rate by adding some contribution from potassium 40 in order to know what is the level of potassium 40 that we can tolerate in the detector. And for the sensitivity on the effective neutrino mass, this is with the background that I present you. This is what we could reach in 10 years of data taking. And at the end, okay, I come back to the sensitivity. What will be today we could reach if we have this 1.6 event, 1.6 background events per year. We will reach this sensitivity with 600 kilograms. But if we can reach no background, in this case, we will reach this sensitivity. And in fact, with 2 tons and no background, we can rule out the inverted hierarchy. So it means that in the future, we could reach the best sensitivity. And this is a comparison with the existing project. So you can see that we have here the NEXO, we have a Legend, and we have a Cupid. And we could be in the rest in the future, because today all these experiments have the problem with the background, and it will take time also for them to solve this problem. So in conclusion, we have demonstrated that the concept of cylindrical TPC is working. We think that most of the technical issues, like gas purification or circulation, can be based on the base of the know-how that we developed for R22, but also for the solutions that exist in the Xenon community. Now, what is very promising is the development that we are doing with the industrial in order to get a low radioactive composite. And also something which is very important is that we are not using cryogenics. And it means that we have a very low energy consumption, and the detector is very cheap. and the operation will be also very cheap. So this is a current collaboration, and it's not a current because we have now people from Prague and Bratislava who join us, and so we have still a lot of work to be done to develop and to build the final detector. So all people who are interested to join the R2D2 effort are welcome. And thank you for your questions.